When an unauthorized data transfer hits a network boundary and shatters against a firewall, you are watching the final step of a much longer process. Technical controls like firewalls, encryption algorithms, and access brokers do not operate in a vacuum. They execute a predefined organizational policy. This is the core objective of the asset security domain. It requires protecting information from the exact moment it is created until the moment it is permanently destroyed. To actually protect an asset, a security architect has to classify its value, identify its current state, and map it to a rigid, deterministic security matrix. Information security is a governance problem that is solved through engineering. Before an organization can assign a classification, it must identify its sensitive data. This is any information that requires protection because of its internal value or strict legal compliance mandates. The first major category is personally identifiable information, or PII. The National Institute of Standards and Technology officially defines PII as any information that can be used to distinguish or trace an individual's identity. A similar category is Protected Health Information, or PHI. The Health Insurance Portability and Accountability Act is a U.S. law mandating the strict protection of patient health records. This mandate applies to direct healthcare providers, but it also extends to health insurers, clearinghouses, and any employer that provides health insurance. Organizations also hold proprietary data. This includes unreleased software code, technical plans, and trade secrets. If a competitor or a threat actor gains access to this data, the organization loses its competitive edge. Failing to formally categorize and protect these specific types of data leads directly to regulatory penalties and financial ruin. Once the sensitive data is identified, the next operational step in the data lifecycle is classification. This process mathematically defines the potential adverse impact on the organization if that specific data is breached. This pyramid diagram compares the formal data classifications used by the government with the models used by the civilian sector. In the United States government, terminology is rigidly constrained. The top secret label specifically equates to exceptionally grave damage. The tiers directly below it follow exact linguistic definitions. Secret data dictates serious damage, and confidential data dictates standard damage. The civilian side mirrors the structure. Private organizations frequently use the confidential or proprietary label to denote their highest level of exceptionally grave damage, like the theft of an unreleased product line. Below that, the private tier holds personally identifiable information, mapping to serious damage. The sensitive tier contains internal operational information, like network layouts or IP addresses. At the very bottom is the public baseline. The organization does not protect the confidentiality of this data, but it still must protect its integrity. Data classification anchors the entire security model. It dictates exactly how much capital budget and operational friction an organization will tolerate to protect a specific asset. These classification rules apply to the physical infrastructure exactly as they apply to the intangible data. Hardware explicitly inherits the classification of the most sensitive data it processes. If a standard off-the-shelf server begins processing top-secret data, that physical server immediately becomes a legally designated top-secret asset. Because of this inheritance, security personnel apply prominent physical labels to monitors, hard drives, and backup tapes. These labels constantly remind users of the asset's criticality and the handling rules that apply. A secure enterprise architecture requires the physical hardware environment to perfectly reflect the risk profile of the digital data it holds. Data vulnerability is not static. Throughout its lifecycle, data constantly shifts between three distinct states, each requiring specific cryptographic controls. Data at rest refers to information stored on media like solid-state drives or storage area networks. Solid-state drives use integrated circuits to store data persistently, and storage area networks are high-speed architectures providing block-level access. The primary control here is strong symmetric encryption. Data in transit is any information moving over a wired or wireless network. Security architects protect this state by implementing transport encryption protocols to scramble the data before transmission. Data in use is information actively being processed in temporary storage buffers, or RAM. RAM is the random access memory, where a computer temporarily stores the data it needs to execute current tasks. This is a highly vulnerable state. Standard applications must decrypt the data and place it into memory in clear text so the processor can work on it, leaving it fully exposed to memory scraping attacks. Engineers mitigate this by immediately flushing RAM buffers when a task completes. Emerging technologies like homomorphic encryption also allow applications to process data while it remains fully encrypted, eliminating the clear text vulnerability entirely. Homomorphic encryption is a cryptographic method that permits computations to be performed on ciphertext with ever exposing the underlying data. An attacker only needs to compromise the data in one of these three states. Security controls must seamlessly hand off to one another without leaving any structural gaps. With the data classified and its states identified, security architects map the theoretical classifications directly to rigid technical controls. We can see this transition clearly by looking at enterprise email. This table outlines a predefined security matrix for handling email data across different classification tiers. At the baseline public classification, organizational policy allows employees to send emails and attachments in clear text. Moving to the highest tier, confidential proprietary, the technical constraints scale up aggressively. The baseline requirements for this tier mandate AES 256 encryption. The advanced encryption standard with a 256-bit key is a highly secure cryptographic algorithm used globally. Additionally, the system restricts routing exclusively to recipients within the internal organization. The matrix also enforces application-level behavioral constraints. Users are technically blocked from forwarding the email, copying the content, pasting it into other documents, or printing it. These rules directly address the three data states. The AES 256 algorithm protects the email at rest on the server and in transit across the network. The restrictions on copying and printing protect the email while it is actively in use on the recipient's screen. Security teams duplicate this exact matrix approach for all asset types across the enterprise, applying corresponding rules to databases, file servers, and cloud storage environments. A mature security matrix removes human guesswork. The assigned classification label mathematically dictates the exact architectural constraint. How does an organization actually enforce this complex rule matrix across thousands of users at scale? They deploy data loss prevention solutions. DLP systems are automated software tools designed specifically to detect and block data exfiltration attempts. The core capability of a DLP system is scanning unencrypted data in real time. It actively searches files and network traffic for specific keywords, metadata labels, or numeric format patterns. If a user attempts to email a document containing a 9-digit pattern matching a U.S. Social Security number, the DLP discovers it. It automatically triggers the private data rules from the security matrix, blocking the transfer. To ensure total coverage, administrators deploy DLP solutions across three primary operational vectors. First is network DLP. Security teams place this at the perimeter edge to scan all outgoing traffic and block unauthorized sensitive data before it leaves the corporate network. Second is endpoint DLP. This software is installed directly on user systems. It monitors localized actions, physically preventing users from copying sensitive files to a USB flash drive or sending them to a local printer. Third is Cloud DLP. Organizations utilize this to discover, classify, and protect data hosted in external cloud infrastructure. DLP does have a critical technical limitation. While the system can easily inspect inside compressed zip files, it is completely blind to data that a user has already encrypted. The asset security lifecycle forms an unbroken loop. Governance categorizes the risk, cryptography secures the state, and data loss prevention enforces the boundary.